I'm Ehsan, and I'm here today with my colleagues Manoj and Chris to talk about memory requirements of Meta AI workloads. So AI workloads run across many applications and services in Meta at scale. And as a result, they tend to drive a portion of our infrastructure, both in terms of hardware and software. When we are talking about AI at very high level, we kind of see AI applications and workloads in two slightly distinct categories. One are ranking and recommendation models. These are the models that, for example, rank and suggest what kind of, for example, videos would be matching a particular interest of a particular user. And the other category is content understanding, like the classical computer vision, machine translation, so on and so forth. The reason that we see them as two different categories is primarily because of different ways that they utilize and they stress the underlying system. In this talk, we are particularly focusing on the AI application and workloads that runs on data center. So the challenge that we have with AI workloads is the rate at which they scale. The two plots in this slide try to essentially demonstrate this point. The plot on the left is trying to show the rate of scaling of a range of AI workloads across years. And as far as the compute requirement of these workload concerns, the y-axis is petaflop per second day is a metric of compute intensity. And mind you that the y-axis is actually in logarithmic scale. So we see a linear scaling of the model as we go through years to right, which indicates an exponential scaling of the compute requirement. On the right plot is again the same set of workloads across over a few years, but we are here tracking the number of parameters that we have per model. And the number of parameters to a good degree correlates with how big the model would be. So what is the memory requirement? And maybe loosely correlate with how much memory bandwidth we would need. So on the right plot, essentially at the top, you would see DLRM, which stands for Deep Learning Recommendation Models. These are the models that really are pushing the envelope in terms of the memory bandwidth and memory capacity requirement. And on the left plot, in terms of compute scaling, it's content understanding and the likes of GP3 models that are driving essentially the requirement. So the particular challenge that we have here is the rate of scaling, which is faster than the scaling of technology, underlying memory technology. So because the scale is faster, then we have to come up with intelligent ways to try to get as much as possible from what we have available at our disposal. One of which would be more vertical integration from software requirement all the way to hardware design. So a few points regarding essentially these recommendation models, which, as I mentioned, they're really memory bound and they're pushing the envelope as far as memory capacity and memory bandwidth per system goes. So they are one of the main drivers of the AI hardware platforms. And a couple of points that I want to point out here regarding these models is, one, there is a clear distinction that we could make between the portion of the model that is compute intensive, we call these essentially dense part of the models, and the portion of the model that is memory bound and stresses the memory, we call these sparse part of the model. You might hear me talking about embedding tables and whatnot. Essentially, the memory requirement of the sparse models is materialized through what we call embedding tables. We can essentially see them as something similar to a lookup table. That's why they have a huge capacity requirement and as well as memory bandwidth requirement. And one last point to make here is DLRM is a class of use cases or class of workloads. Specific use cases would materialize in slightly different shape and form, but all of them adhere to the same kind of architecture for the foreseeable future until things start change. There is quite a bit of information packed in this slide, so let's spend some time to unpack the information. So having talked about DLRM and the fact that they are pushing the envelope as far as memory requirement goes, so we want to essentially lay out what are these requirements here. And when we are talking about memory, of course, we want to talk about bandwidth as well as latency. So the two plots on the right are trying to lay out the bandwidth and latency requirement. And essentially x-axis here in these plots, you can see it as trying to carry a notion of capacity, memory capacity, and the y-axis would be bandwidth and latency for top and the bottom charts respectively. So on the top chart, let's look at the point highlighted with number 1. So what we see here, or what we are trying to get across here, is that there is a considerable portion of these recommendation models that requires very high memory bandwidths. That area we are highlighting as accelerator memory, aka HBM. So there is a good portion that would require HBM. But looking at point number 2, which is at the bottom of the top chart, we see a considerable portion of the capacity that actually does not require very high bandwidths. And the memory bandwidth requirement is, in fact, less than main memory bandwidth and getting close to storage class memory kind of bandwidths, which is a good sign. Typically, with memory system, we can get everything at the same time, and such characteristic of the bandwidth requirement would help with our system design, and that's what we are trying to allude to in the following slides. But bandwidth is not everything. We also need to talk about latency. The main point to take away from the latency chart, the chart on the bottom, is the fact that there is a very narrow band of latency. Essentially, regardless of what type of memory capacity we are talking about, everything required low latency access. And in terms of the latency itself, the application is tolerant of slightly maybe higher latency than main memory, but these applications do require shorter latency compared to, for example, the storage class of latency. All right, what are the takeaways here? Given the fact that essentially we have a considerable portion of these applications requiring very low bandwidths, then a tier of memory beyond HBM and DRAM could be leveraged to help cope with the extra capacity that these models would require. The higher latency, the latency requirement of this tier of memory could be higher than main memory. As I mentioned, the application is tolerant of slightly higher latency, but it's still the semantic and the latency profile would be very similar to a typical memory. For example, like TLC NAND flash here does not work given the skewed loaded latency that you would get with those technologies. The other point to make here is that we are primarily shooting for capacity, and as such, we could trade off some performance for density. And here where actually Optanes come to the picture as a good example of providing such trade-off for this application. So note that all of these does not negate the fact that we still would like to have higher capacity, faster main memory and HBM memory. We are talking about something in addition to those to cope with the scaling of the memory capacity. All right, how does all of this fit in the whole end-to-end system? The primary way that we track the impact here is essentially perf per watt, meaning that we want to provide the application, the workloads with what they require to satisfy their needs and maintain the performance, but try to do that with as low of power consumption as possible. And that by extension could also lead to perf per dollar, which, as I mentioned, these are the main metrics that essentially we would follow as for the end-to-end system. There are different ways that such metrics would be materialized, or the gain on those metrics would be materialized. And in next couple of slides, I would try to go through some of the examples that we have tried at Meta. So the examples that I'd be going over, they are published in a paper titled Supporting Massive DLRM Inference Through Software-Defined Memory. It's available, and you guys can look it up. The main points that I want to have here is that essentially this work particularly uses essentially NVMe attached memory, SSDs, as the only feasible solution at the time for this new tier of memory that you would like to have to scale memory capacity. Based on the demands and requirements of the workloads, the typical NAND flash would not satisfy the requirement across the board. So something like Optane SSD with higher I/O rate at smaller granularity was something that enabled the use case across a wide range of workloads, DLRM workloads. And in terms of the actual implementation, we do have application level caching in memory. So we can capture as much temporal locality as we can in the access to the embedding tables of the models. And of course, given that this is inference of the recommendation model and latency is very important. So fast IO and such is important here. There are also good level of optimizations as to how we decide what goes into the main memory and what gets mapped into the new tier of the memory, the capacity tier, based on the information that we have about embedding table as to how big they are, how much memory bandwidth they would typically require, what is the locality to those tables. So it's kind of an optimization problem that we can have to improve the performance. So
before you go on any further, can you put this into a little bit more plain English as to why we'd be interested in this? I mean, it's very technical and it's extremely deep, but so what?
Right.
Can you put it into, kind of like, high school level IT discussion?
Sure. So there are two kind of main reasons why we actually want to look into this. One at high level is that we get to a point in future that the amount of memory capacity required by model is such that we cannot actually serve them, right? So that's one fact. The other is that if we want to essentially serve these massive models just relying on, for example, DRAM technology, that leads to a system design that is not necessarily optimized for performance per watt. So we do want to essentially leverage the characteristics of the model, the model's tolerance to denser but the slower type of memory such that we can just design a system around that with better per watt characteristics.
Okay, that makes sense.
Are you able to let us know, like, any kind of very broadly describe the model in the beginning, but just kind of, since we've heard all of the technical back end of it, again, can you remind us again which models these are actually supporting, and maybe kind of the requirements of the model itself and the outputs of the model?
Sure. So these are recommendation models. They're known in public and academia as deep learning recommendation model. That's the way that Facebook has open source, so the community would be able to work on such models. So in terms of use case, you can think of it as the models that would try to find relevant news feeds or relevant ads for a particular user. Right. So the input is like you have a user and you have a range of, for example, videos that you want to at the end of the day find maybe 5 videos that is most relevant to the user. A couple of scenarios that actually we have worked on and show improvement in the power. First scenario, essentially what we do is that we are taking one of these production recommendation models, and we show that essentially we can deploy or serve these models with a simpler hardware and save power. So the model is, as I mentioned, is a production model. The model itself is not, it is about 143 gigabytes, and we typically serve such model with a dual socket system, mainly because the dual socket system comes with a high memory capacity. And we do need this high memory capacity so we can actually load the model. So the capacity is more than 143 gigabytes, which is the model size. So the baseline runs this model at about 240 query per second. Alternatively, we can use a single socket machine with much smaller memory capacity. The memory, in fact, is much smaller than the model size, but we can leverage storage class memory as the last tier, the capacity tier for memory, and load the model into that last level. So what happens is that with this simpler hardware, we get about half of the QPS of the baseline, but we are matching the latency of the baseline. So for the end-to-end use case, we need to, given that we are getting half QPS, we have to double the number of hosts. The catch is that the simpler system has less than half of the power consumption of the baseline, has 40% of the power of the baseline. So as an end result, we come up ahead with 20% saving in power, right? The second example that I want to go over very quickly is another case of a production model. This is a model that is much denser in terms of the amount of computation that it would require, and it's still a very large model. It's 150 gigabyte model. Because it's dense, it relies on accelerators to essentially get deployed and get served. But these accelerator-enabled platforms don't have enough capacity to fully load the model. So what we need to do as a result is to scale out to some other type of machines such that we can bring more capacity to the use case, right? The alternative solutions that we have tried here is to use NAND flash as the last tier of memory, don't do scale out, still by loading the model into NAND flash, we could have the model in one host. But in that case, in case of NAND flash, we have to really underutilize the NAND flash to hit the latency requirement. So as a result, the QPS really drops and the power actually gets worse, not a desirable solution. By using Optane SSD, given that it's is much faster in terms of I/O per second, and it has better latency profile compared to NAND flash, much closer to a memory. We can match the QPS and still load the model, avoid the scaling out, and as a result, essentially save all the extra power that we would have consumed the scaling out and going to a different tier of the host for memory capacity. So that allows us to save about 5% of end-to-end power with such solution. And a byproduct of that is actually the serving system is much simpler right now, because a query just go to one host and it's done, rather than scaling out and spreading to another set of tiers and the complications that come with that. Any questions?
Yeah, so when you say power, do you mean literally electric power or some other thing?
Yeah, that's a good question. This is watt. So we are talking about power, let's say amount of power that we need to serve the end-to-end workload, which means like maybe thousands of hosts have to participate to support the traffic that is coming to a particular data center or whatnot, right? So this is watt that we are talking about.
Watts. Okay, thank you.
And so just to put it in terms of the application and the consumer consumption of it, the scale out would come if there's a really hot new trend or an election or, you know, a political uprising. Mm-hmm. So is that when it would come, when you would have to decide between all of the amounts of videos that are out there, which are the 5 best for a particular user?
Mm-hmm. That's a good question. And the answer to that is no. Regardless of how hot a particular trend could become or whatnot, for any single query coming to the system, we need the whole model. And needing the whole model, we have to get involved essentially all the components of the infrastructure that holds the model. Okay. So regardless of if something is trending or not, a particular request has to essentially go through multiple different hosts. One is the main compute host, and the other one that is giving us extra memory capacity.
Oh, okay. Okay.
Yeah, maybe I can pile on here real quick. So I think fundamentally, when we look at designing systems to support our infrastructure, there's a couple of different approaches we can take, right? So in this example, if we have a 150 gigabyte model, if one of the servers that we're designing can only support 100 gigabytes, we really only have 2 options that we can design for, right? Either we have to take that model and put it on 2 servers and we split it in half, right? So that we get 200 gigabytes to support that 150. Or we have to find some other way, for example, by tiering memory to expand the capacity on that machine. And so when we talk about scale out, that's when we're talking about multiple machines serving a model versus just one.
I'm Manoj, and I'm in Meta looking at all our storage and memory products and roadmaps for technology for the next generations. What Ehsan has established and Chris talked about is that as we see this need for storage layer that now provides load store interface, we have a layer now that is sitting between the DRAM and a NAND, but we want a load store interface. We are ready to trade off certain throughput and latency as we looked at the inference use case. So the standard storage pyramid is now becoming a little more granular. And we talked about that before also, that there is a layer between DRAM and NAND, and CXL is now looking forward. CXL is enabling this kind of a capability for memory expansion in a standard fashion. So these CXL attached memories can provide a scalable and a heterogeneous, with different types of memories can come together to provide a scalable solution, which actually you can create what Chris talked about as hierarchical memory or tiered memory to achieve that kind of a larger scale of memory within a single system that allows us to not to go to the scale out model that we talked about. So there are the 2 types of such memory expansion needs, just focusing on CXL, but then I'll come back to the AI specifically. There will be applications which will require memory expansion, but they're not necessarily trading off a lot of bandwidth. So they'll be closer to DRAM. Let's call that the CXL bandwidth memory, which is allowing you to increase memory a little bit, but not trading off the bandwidth necessarily a lot. But AI use cases really fall into this second bucket, which is CXL capacity memory, if you will, which needs a very large capacity and is ready to trade off the throughput and some level latency, as we talked, as Ehsan talked about that pyramid, about where inference comes into as it's closer, a little bit closer to the storage, a little bit away from the memory. So we are ready to make that trade-off. And this is where we see a need for a new type of memory that is coming along that CXL is enabling. And keep in mind, this is not necessarily the capacity memory in lieu of DRAM, natively attached DRAM. This is basically tiered memory along with the DRAM and multiple solutions that allows us to get to that larger capacity memory that we are trying to look for. So we need this kind of a larger capacity where we are ready to do the bandwidth trade-off. And we have been starting to focus, CXL has done the work for enabling such technology that products can come to the market. In OCP, we have started looking at a future technology initiative where that's chartered specifically to drive these end user use cases like the one which we talked about just now, and enable the product community dialogue so that we can get such use cases for tiered of hierarchical memory to make sure that we can drive the market also with the enough information for how this will be used and what can be done with the products that if such things come to the market. And AI ML use cases are driving need to store data per node to avoid the scale out model as we talked about. And this is feasible as I showed in the previous slide to achieve with the efficient TCO if we had the right capacity memory solution. So to summarize, if we see what we are saying is that these AI models are driving our need. They are scaling faster. They need more changes in this underlying memory technology. We have a large gap right now between the DRAM and NAND from the performance perspective. Even though the tiering solution that we currently looked at does explore that as the paper was published. And as far as the memory capacity is concerned, we do need that additional tier of memory beyond what the host memory has today so that we can expand that through that capacity memory and achieve the desired density through the capacity memory. And CXL is a great way. This is the standard way that allows us to get to that through the load store and not necessarily pay the penalty for latency by going through the block interface. That's what we can get to through this new memory tier for the capacity memory. And the good news, of course, to get to the right TCO model, this memory tier can trade off some performance for capacity. And we believe Optane memory is an example for that. So we look forward to CXL and such technologies enabling us to do these greater things as we continue to see explosion in our AI models for the capacity.
Manoj, as you using this tiered memory, this is presumably putting a load back on whoever's developing the software that's running on top of this to identify which parts fit in which place. Can you address that a little bit, or is somebody else on the team better placed?
To enable such tiered memory, of course, there is work required in many places. There is a work required many times in kernel, which is a preferred way, which allows applications to take advantage of such tiered memory in a transparent fashion. There could be applications that will come up and start taking the advantage of it themselves and may be more efficient in future, perhaps. But I think both those models will continue to evolve. Of course, the kernel, there is a lot of development and there is a lot of buzz and a lot of activity going on in the kernel space right now. Meta is involved in it. Many companies are involved in it right now. So we definitely see a healthy innovation in that area. Chris or Ehsan, would you like to chime in anything?
Development in kernel means that it's shared across every application, only has to be developed once, and all of the applications benefit from that.
Right,
yes.
Not necessarily optimizing any particular application.
Yeah, I think to Manoj's point, there's need for both, right? I think there is clearly some applications that you can put the energy in and do some additional optimization work. And that is already happening. But at the same time, as Manoj alluded to, honestly, having a transparent capability so that you don't have to make application changes is also extremely valuable, right? Even for us, right? We cannot optimize every application. It's just not feasible. And so one of the approaches that we're taking is to do that at the kernel level. The memory allocator is actually pretty intelligent and we're only making it smarter, right? So if it's smart about what pages it puts in different pieces of memory tiers, then that may be good enough.
You said you can't use a RAM like this DRAM for the model, right? You only use like the SSD, that is the Intel SSD.
Right. So So there are, one main point is that if you could use DRAM, right, that would, the system that you're designing around that solution essentially ends up at a particular, let's say, performance per watt point that is not as optimized as a case that you have a solution that leverages memory technology that is cheaper and have better power compared per gigabyte of memory, right? Essentially here we are arguing for trading off performance for capacity and whatnot. And as a result of that, we expect to have better power per gigabyte of memory capacity that we are providing to the application, right? So that's one point. The other point is that considering the rate at which these applications are growing, the relying on HBM and DRAM is likely not going to be enough, right? Because we are scaling faster than DRAM technology is scaling. So we need to jump into a different swim lane to gain more capacity, if that makes sense.